Well, hello everyone. Thank you for coming along to my talk today, which, as usual, is called The Application of Commercial Supercomputing to Next Generation Radio Astronomy. And just to start, I want to acknowledge that this work is jointly funded by Curtin University, CSIRO, and Doug Technology. Now, next generation radio astronomy. Now, as we all know, radio astronomy is critically dependent on high performance computing, and particularly in two areas. There's the extraction of visibility data from the field data. That's the work that gets done at the correlator. And then there's the imaging and other analysis, which gets done at the SIRS data processor and other computers that researchers might have access to. And as we all know, the area is getting an order of magnitude upgrade with the advent of the square kilometre array, which is currently under construction and being built out over the next 10 years or so. And throughout the planning and design of the SKA, there's always been this concern: will we have enough high-performance computing to deal with the tsunami of data that's going to be coming from the new instruments? And in fact, oops, sorry, I got the wrong slide there. In fact, back in 2011, this image here is from a paper by Ray Norris, 2011, where he referred to the SKA data challenge. Now this chart is based on data from the top 500 supercomputing list, which is a biennial survey which has been produced since 2013. And this middle line here is basically the computing power of the top supercomputer in the world on that list. And Ray's story was basically that going through ASCAP development, ASCAP implementation, when they get to SKA phase 1, which is what we today are calling the SKA, the computing needs are going to be like pushing the boundaries and nearing what's achievable with the world's largest supercomputer. And by the time they get to the fully built out system, SKA phase 2, the computing needs are going to be well above what's available with what's expected to be available with supercomputers worldwide. Now, this data challenge, to a certain extent, has been mitigated by the delays in the start of construction of the SKA. So this is the same top 500 data, but it's actually updated for 2023, and you can see that the top machine lineup here is still going up exponentially. But what's happened is that the SKA commissioning dates have gone out to the right. So by the time the SKA phase 1, which we're calling the SKA, by the time that's actually available, the computing requirements should be well within machines that are in the bottom end of the top 500. So I mean, Cytonics phase 2 is sort of already there and probably has the capacity to run most of the SKA low data processing. SKA phase 2, well, there's no real dates attached to that yet as to when we're going to get that infrastructure, if ever. But assuming that comes like another 10 years later, again, I'm looking at the sort of extrapolation of this line here. The computing requirements should be well within what's achievable with, fairly good top-end supercomputers at the time, but there's no longer a challenge, or there's no real risk of not being able to meet the computing needs. In fact, I've done quite a bit of work with this top 500 list, and as has been pointed out before, the data has its problems. There are a number of issues with the list, but it is an unbroken survey from 2013 using a consistent methodology. So I would say it's good for detecting industry trends. I mean, some of the exact numbers in there may be debatable, but for looking at trends, it's quite a good resource. And the main trends which I've picked out looking at this list over the last year or more is that high performance computing is still increasing exponentially. So that log curve, like I just showed before, is still continuing. And there's an increasing penetration of commercial providers into the upper reaches of the top 500 list. So whereas previously that was the preserve of government, major governments and large research organisations, we're seeing cloud providers and other commercial providers being able to put together systems that fit into the top 500. Australia is following the international trend, so even though our top machines tend to be down the bottom of the top 500 list, they are still going up on that roughly that same exponential curve that we're seeing globally. Well, here's a single number just to stick in your mind, just one number to remember, which is if you look back over a 10-year history, whether you're tracking the top machine or the number 10 machine or the number 500 machine, approximately HPC capacity increases approximately by a factor of 40,000. So we might expect that 10 years from now, we'll be using machines which are 40,000 times the power of what we're using, of what we're used to using today. So that's what I mean by exponential growth, and it really leads to my thesis. My underpinning my thesis is that an alternate future. So instead of having a challenge, we can't get enough supercomputing. I would like to put forward a different picture, which is that maybe 10 years from now, we're kind of surrounded by an ocean of high performance computing and cheap and plentiful supercomputing, and not just in the government funded systems. We can expect to see an ecosystem of commercial providers, multiple commercial providers possibly competing for customer, maybe coming to us as astronomers, looking to get us as customers and offering various things, various services and so forth, because they want us as paying customers because we're big data people and they all need to earn their living. Now, if this is true, and if we have this large and plentiful supply of supercomputing, that perhaps can enable new science to be done that can't be done today, because if radio astronomy is no longer constrained by high performance computing, what could we actually do if it's effectively unlimited? We could do new types of analysis. There could be a faster turnaround of ideas. So from having an idea to getting your observations to analysing your observations and publishing a paper, shortening that whole workflow. So effectively, astronomers can have more productive careers because they can produce more publishable material in those critical years in between, in between finishing your PhD and becoming a full-time manager at ICRA. I think that 10, 15-year window you've got to really, really pump out the research there. So that's the basic picture of my thesis. And really, to understand what that future might look like, the question really is, what would have to happen for astronomers and HPC providers to get together to actually realise that improvements in the processing and shortening the life cycle of projects in the astronomy space. And so I've got a list up on the board there of the questions which I'm looking at in my research. We're not going to run through them all, but basically some of the important ones are things to do with technical support. So how easy is it to establish your astronomy tools and your workspace, get it up and running on a new platform, on a commercial platform that hasn't necessarily, where the technical support team aren't necessarily astronomers, they don't necessarily understand your specific issues with your specific data. Is it easy to install the tools? How are you going to do the workflow management? You might have to learn other tools apart from Slurm. What about physical transport of data and the version management? Once we're taking data away from the repositories at the telescope or systems like CASDA and so forth, how do we keep track of the data, and does it become a bottleneck? And right at the bottom of the list, of course, we've got the standard things which you probably think of first, which is what's the runtime of the system and what does it cost? So we've got those things as well, but it's more about the more intangible aspects, I think, is really what's going to affect or impact the uptake of commercial supercomputing by astronomers. Oh, sorry, let me just go back. So in my PhD work, I'm setting out to get answers to some of those questions in a practical way by doing a small number of case studies in astronomy, perhaps up to 4. So here I am at the moment 18 months in, and we're well on the way towards completion of two case studies, and I've got a third one probably just about to start. I've still got room for a fourth one in my fourth year of my PhD work. So now I just want to just go on and describe the case study. So case study number one, which I'll talk about, is the GasCap H1 survey. GasCap is an international collaboration of researchers using the ASCAP telescope to survey cold gas in the Magellanic Clouds and the associated structures, the bridge and so forth that's there. And I guess the current state is that the data from the telescope is really in the form of visibilities that get published from the ASCAP science data processor, and mostly the researchers have been downloading those gigantic visibility files and taking them back to process them at their institution's computers. That's the way people work today. The intended future state for the SKA is to do more of the work at the science data processor. So the intention would be, the model would be that these more specialized images would be produced as part of a standard workflow on the science data processor, so that researchers would use those as the starting point and not have to build their own images using the visibility files. So the software to do this specific type of imaging that's used in the GasCap survey is still under development. It's a growth of Yandersoft, which is currently used at ASCAP. So my part of the work, my case study, the technical goals were really to produce some images using the Doug supercomputer, using this technique known as joint deconvolution. And we would use that to provide benchmark data, images and runtime information for the upgrade to Yandersoft. That's really the underlying purpose of it at this stage. Now, joint deconvolution is a very memory-hungry process, but it can be done at Doug using their Intel Cascade Lakes nodes, which have quite large memory on the node. Now, previously, this kind of work, the researchers would have done this work by forming images from each of 108 beams. That's 36 beams at 3 interleave positions, gives you basically 108 beams. So the researchers would produce 108 images and then mosaic them all together to produce the large cubes that they need to start doing the research on the Magellanic Clouds. So with joint deconvolution, you take advantage of the large memory on the node to process all 108 beams simultaneously. So you're basically taking in a bunch of 6 terabytes of visibility data and producing a 150 gigabyte image cube. That's kind of what you're doing. And doing this on Doug, one run takes about 3 weeks to complete. So what you end up with is a 5,000 square pixel image with 2,000, a little bit over 2,100 channels. And so I've been working on this one. The first part of the work, I guess, was mainly upgrading the workflow. So there was an example cookbook that had been produced at the Australian National University that I started with. So it's a case of taking each of those stages, optimizing them to run on the Doug supercomputer, and carefully recording, the run times and any issues that come up in terms of making images, so we can really provide that data to CSRO. So when they're replicating the process in Yandersoft, we can see whether it's more efficient, less efficient, and check that the images are the same sort of quality that we've been getting here, that the science team found acceptable. This picture in the background is one frame it's one frequency. It's one frame from an image of the small Magellanic Cloud. In fact, I've got a video here. I'll just play this video and I'll talk while it's running. I'm not sure how good this is going to come out on the for people online, but the video is running now, and what we're basically doing is stepping forwards through the channels from the lowest frequency to the highest frequency. So, and you can see a couple of continuum sources there in the middle of the image there that kind of show you that the phase center isn't actually moving, but you'll see that the bright areas where the H1 emission is slowly moving from left to right in the image, which basically tells you that the gas towards the left-hand side of the image is less blue shifted than the gas to the right. So overall, the gas on the right-hand side of the picture is all moving towards us. You also see these dark holes in the image there, where there's no emission at certain frequencies, but then the holes get filled in, so there is emission at higher frequencies. And that shows you these black holes, they actually represent channels where the gas is either flowing towards us or flowing away from us. And with just the distribution of emission at different frequencies, you can see there's quite a lot of turbulence and motion in the gas. So this is what the science team are looking for, because they want to analyse the overall structure of this. They want to look at these tiny little filaments you can see there in the image and how they relate to the history of the formation of the galaxy and its previous collisions with the Milky Way. And also, I mean, do research like look for correlations between the gas turbulence and the star formation rate, which they're going to get from optical astronomy. So that's an example of what's been doing, and that's what I've been working on with the gas cap guys. And so at the moment, the sort of outcomes of the study at this stage are that we've got one complete cube that's been done right the way through to the end of the process. So we've got a benchmark image, and we've got run times. They've been supplied to CSIRO to benchmark their implementation of this workflow. We've demonstrated the capability that's available right now using DUG, and the images will be used for many studies. And in fact, they're because the software to do joint deconvolution isn't ready yet at PhD, the science team are actually looking at potentially doing the image processing from their phase 2 survey with a sort of slightly more automated version of my pipeline at DUG. So that's the outcomes of the case study. In terms of my PhD work, I've been documenting the interactions between the science team and the HPC provider. So we've got some concrete data on what it's like for astronomers to go along and try and work with a commercial provider. I've got data on the speed and effectiveness of technical support, which has been very good at DUG, and also looking at the data transport issues, which a number of people were very concerned about at the start of this project. Initially, it was quite difficult to transfer data from PhD. And in fact, DUG have actually come along and they've actually provided a script to do a kind of drip feed of data from PhD into the CSIRO workspace. So again, that's an area where the technical support guys have come in. They've provided us with an additional capability that I probably wouldn't have been able to develop myself. And as I mentioned, we've got runtimes as well. So that's probably all I want to say about that particular case study. And now I'm going to move on to case study number 2, which is searching for fast radio bursts in the data archive of the Murchison Wide Field Array. It's with the MWA. And this work is a scale-up of Professor Tingay's 2015, or work that he published in 2015, where he searched 10 hours worth of data from the MWA archive using an image-based method, looking for fast radio burst candidates. I think probably more than half the people in the room here are actually working on fast radio bursts, so you're probably familiar with this work, with this paper. So the first thing I needed to do was basically take Stephen's scripts and so forth and basically reformulate the thing as a massively parallel problem so that we can actually scale it up on the supercomputer and search a much larger volume of data. So initially I used a range of tools on this data. We tried initially using CASA. I had a few issues, so I switched over to using WS Clean a bit later in the process. Initially I reprocessed Stephen's 10-hour data set that he used in 2015 just to check we're getting comparable results. And then we went ahead and to process 100 hours of observations from the EOR0 field. So I've shown this slide before in a couple of other forums, but the basic unit of computation here is a 1 megapixel image cube with 24 channels. So basically we took the whole 100 hours worth of observations and chopped the whole thing up into 2-second snapshots, which is what's shown on the top row there. The next step is to use difference imaging to produce difference images, again, for the whole 100 hours worth of data. And finally, you can produce these dispersed images by, you think of a trial DM value, and then you go off and you pull out the slices of data corresponding for different frequencies, corresponding to the different time steps you need to de-disperse the information. So you end up with 100 hours worth of de-dispersed cubes for each trial DM value that you want to try. And so in my study, we used 24 different DM values. So here's an example of a good, sort of around about 80% of the images come out looking a bit like this, which is just really random, just noise, an image of the noise. And from the scale there, you can see that they range from about +3 to -3 sigma. That's the sort of range in the data there. But around about 20% of the images were giving 7 sigma detections. So there's an awful lot of false positives in there. So a major part of my work has been to characterize the sources of those false positives so that we can detect them and reject them early in the workflow before then actually starting a search for fast radio bursts. So here's I've got a couple of examples of some of the defects we saw. So one of them is where you've got missing data or flagged data, and when that happens, your radio sources here, the static sources, come through they survive the differencing process and they bleed through into the de-dispersed image. So easy to recognize, easy to remove. Radio frequency interference comes in many different forms. Here's an example of one of them. Again, this particular type is very easy to pull out because you get an excessively high RMS signal, easy to find. Around 8% of the data is affected by scintillation. And what happens when you've got scintillation is shown in this diagram here. So this is showing from 1024 by 1024 pixels. And this is not just for a single 2-second snapshot. This is for a collection of about 400 snapshots all smerged together. And I've plotted all the pixels which are above 6 sigma on here. So what you see is that some of the sources now become visible because the differencing process doesn't quite take them out. And instead of being point sources, they become these little clouds, you see, little cloud shapes, because partly because the source itself, the apparent location, moves slightly when the scintillation is happening, but also more significantly probably because the side lobes surrounding the sources don't get taken out by the differencing, and they also move location a little bit. So you get these kind of ray-shaped side lobes coming out from the brighter sources. So those are the things that contribute to these sort of cloud shapes up here. And so the way I deal with these is basically take this actual image and turn it into a mask. So if there's any detections above 7 sigma in the de-dispersed data, if any of them show up inside these these little clouds here, then we just disregard them, they get excluded. So by pulling that out, eliminated most of the false positives from scintillation. Another one was is satellites. So we're getting interference from satellites. So I'll just play this little video here, so you can see. This is just a dirty image. One particular measurement set. I've just taken the snapshots, smudged them together into a video, and again you can see the satellite bombing through the field. And Stephen actually was able to identify this one as being a UCube CubeSat very naughtily broadcasting outside its allotted range. So it shows up as a very bright target. You can even see it's got a set of side lobes kind of travelling along with it in parallel. So it's quite a nasty source of interference. Once I'd actually seen these things and realised what they were, we were able to identify them quite easily because they produce a very large number of 6 sigma detections in the images in the measurement set. So it's once we realised they were there, it's relatively easy to spot them and then pull them out and extract them. So having done that, having then run, so then we run all the data through the workflow, right, pulling out each of these, or filtering out each of these sources of false positives. So I started off, my starting point was 3,024 calibrated measurement sets, which I basically obtained from the EOR team. So Kath's team had already taken this data over to Doug to do their own processing on it, and they'd done a lot of work, fixing up timing errors, flagging incorrect data, and they'd recalibrated everything using hyperdrive. So I started off with a very high quality data set, which gives quite low noise in the final de-dispersed images. So having pulled out false positives, I ended up with about 2,782 successfully processed images. And that total search took sort of less than 5 hours real time. Individual runs were kind of averaged about 20 minutes, but I did them because I didn't want to process everything with one single scintillation mask. I processed all the data in a series of batches using 400 nodes at a time. So there's about 7 or 8 runs, I think, to process them all. And with 24 trial DM values, that gives about 4 million images to do Gaussian statistics on. So on all of those 4 million images, we did we look at the distribution of pixel amplitudes in the X and the Y polarization. So that whole process yielded 122 7 sigma detections. And so I went through and kind of eyeballed all those things, and we've pulled out 28 of them, which may be potentially FRB candidates. And for those of you who work on FRBs, you'll understand this line, which is the sensitivity is not particularly sensitive. It's about 800 millisecond Jansky. So it's not a particularly sensitive probe, but where it is possible to run very large amounts of data. So the strategy here is to use a low sensitivity but search a gigantic data set. And my goal is then to scale this up another step and search the whole of the NWA archive. Even at that sensitivity, you should be pulling up some FRBs when that happens. Now let's just take a look at the results. So here's an example of one of the candidates. So we've got a couple of dozen candidates. So what makes it an potential FRB candidate? Well, the first thing is, now this is going back to that 6 sigma plot I showed you before. The first thing is the location of the thing detection, and I've carefully left its identifier off the slide here. So the location is well away from any of those bright scintillating sources, right? So that's good, that's the thing in its favour. Now these 3 images here are in a time series, so 2-second snapshot, then suddenly we get this one bright pixel there in the middle of this one, and then it shows up in the following 2-second as a negative. And that's exactly what we'd expect to see from a transient when it's being difference imaged like that. So it shows up in one block and then it shows up as a negative on the next one. And if we look at the waterfall plot, so this is now frequency up there, and this is time along the whole measurement set, and you can see the snapshot there that's got the detection in. And this is quite a nice one because it's quite a broadband signal. It's got amplitude right across the detection range, and it's visible in the X polarization and also in the Y polarization. So those are all quite good characteristics which make this one survive as a candidate, which we're investigating. Now, just to contrast that, I'll show you another one. So there's another candidate. Started off looking quite good, but when we do the waterfall plot, you see that all the intensity is in a very narrow band area down here. So it's just a kind of blip at one particular frequency, or sorry, a small range of frequencies. And the other thing is that most of the intensity is in the X polarization, and there's almost nothing in the Y polarization. So it's a polarized signal, very narrow band. That's not really the characteristics we'd be expecting to see in a fast radio burst. So that one we can probably tick that off and say, don't need to worry about this one. So the outcomes of the case study for this one, we demonstrated the ability to do large-scale transient search on the NWA archive using the commercial system with all the data transport and technical support, so forth going on. I've got a definite estimate now. I know exactly what resources we would need in terms of capabilities and time and cost to search the whole archive for MWA. And we may have a handful of FRB candidates. Don't really know yet. We're still deep in the investigation of that one. Watch this space. And again, in terms of outcomes for my PhD, I've got very good data now on how to set up an astronomer-friendly workspace with all the tools that we need. AstroPy, NumPy, and Casa Core, WS Clean, all those things. Getting all that ready, what kind of environment you need. Got good information on the technical support, what the DUG people are capable of doing in terms of helping us get the project up and running more quickly. And of course, we've got the data on the performance and cost of the workflow implemented in CASA and also in WS Clean, so I can understand the pros and cons of those two tools a bit better. We've also got a bit of insight now into the storage and sort of data management issues at DUG as well. So that's the end of my discussion about the case study 2. What I'm doing here is I'm just going back now. This is actually the Gantt chart that I used in my Milestone 1 a year ago. Just the project numbering's changed around, so project 1 and 2 have switched places, but it's effectively the same work. And this basically shows we're pretty much on track with what I expected to be doing when I did Milestone 1. So we've done pretty much towards the end of one case study, well through another case study, and we're just starting case study 3, which is probably going to occupy me for most of next year, of the coming year. And just one thing I'll say is that down the bottom here, there's an item called the Synthesis Cookbook, and the intention there is quite separate to my PhD. I want to produce a little document that explains for an astronomer how to go about using or working with a commercial provider. And this will include everything from in terms of when you're setting up the contract, what services you should be asking for, what a standard environment you need with the tools in it, that kind of thing. What different work options for managing your workflow. So basically everything you need to make it simple to get up and running with a commercial provider like DUG or AWS or someone else like that. And that's pretty much the end of my presentation there. And if this last slide is actually going to come up, I don't think it is, I'm ready to take your questions. Thank you very much.